I'm Aditthya Ramakrishnan, and I've interned at the Media Lab and the CMU. And at my home university in India, I started this lab, which will be focused on student innovation and stuff. So towards the end of this presentation, I'll show a couple of projects we've done using what we'll be seeing today. So even though we're at a PyCon, I'm just going to get this out of the way. The reason people in AI research mostly go to Python or instead of say R or any other thing like Lua, is because of the community mainly. So the frameworks are, the people who make them, the people who use them are really involved, and it kind of every time you ask a question online on any forum or anything, you get immediate responses. So it's much better for also prototyping your ideas quickly. So suppose if you use Keras, you just need to have an idea and you can finish your whole thing in like 30 lines of code. Instead of having to write everything from scratch, which will waste a lot of time for a researcher. You don't worry about kind of optimizing models to work really quickly or something, because the amount of time you'll be wasting on that is huge and you're not building a product. So that's one of the reasons why I use Python mainly. So yeah, what exactly is this talk about? What we're going to do is we're going to take existing data which was written or composed or made by somebody who was dead long ago, and try to see patterns in them and mimic them and create new content based on it. Suppose Mozart died long ago, we can still create music pieces inspired by him using LSTMs, the neural network flavor which we use today. So this is a good example. There's this guy who is a postdoc at MIT CSAIL, and he made this thing in his spare time. So it's basically, has anybody watched Last Week Tonight? It's a TV show. Yeah. So it's called Deep Dump, and it's an LSTM trained on all the tweets of Donald Trump. So since Donald Trump speaks at 5th grade level, it's really easy to kind of approximate what he's saying. So all these things are generated by an LSTM which learn over his tweets. And if you see the output, it's like we have to end education. What they do is unbelievable. How bad. Nobody can do that like me, believe me. So it works pretty well, and I'll explain why it works in a bit. And Karpati is, he's right now the director of AI at Tesla. So he works on the autopilot for the Tesla cars. So he initially came out with this really good blog post, which I suggest you all should check out. It's called the Unreasonable Effectiveness of Neural Networks. So that has a lot of information about how he went about experimenting with those. So a few other examples. Somebody used a Shakespeare data set to kind of create a new play, and people used it on Paul Graham essays, and somebody actually used it to generate actual clickbait. So there's, if you see on the side, Kim Kardashian says idea to a mean baby. I mean, this is generated, and so it sounds funny. So what exactly makes neural networks different, and why are we focusing on them now? Why there's so much hype around it? Is because traditionally, if you see, AI has been going on for a long time, almost half a century, and previously people used not just AI, normal programming itself requires you to distill actual human knowledge into code. So you need somebody to think and actually create those, create the whole thing. So what neural networks do is that you just give it examples and you create some sort of a rough framework for it to learn, and it sometimes outperforms humans at tasks like that. So it creates its own representation of what things should look like. It's more like how, say, kids learn. So kids are really good at learning new things because, if you give them, if you just point at something and tell it's a cat, they will be able to, point out to another cat at a really good accuracy and say, oh, that's also a cat. But if you had to write a computer vision program to do it, you would have to figure out what features are essential to a cat. Is it fur? Because there's some cats, like Persian cats, which don't have fur. So, so that's the thing. And there's, in the last, I guess in 2011, we saw the explosion of deep neural networks. Before that, we had a lot of other things. We had AI winters where no progress was happening because people stopped believing in them. So what used to be there was expert systems and decision trees and SVMs and all those things. So what happened was, there's this really famous paradox by Moravec, Brooks and Minsky. They basically say that the hardest problems for humans to do are easy for computers to do, and vice versa. So if you had to kind of make it, perform really, calculate huge economic models, it's easy for a computer. But it can't classify cats. I mean, at least it didn't used to. So classifying cats is a really hard problem for computers to solve. But recently we were able to kind of fix that. So the other cool thing is that neural networks come into some sort of a new. They basically are changing the entire paradigm of software development. It's like, you can think of it as software development 2.0, where instead of having to distill knowledge and hire engineers to do that work for you, suppose if you realize that what you were doing is not sufficient for your purpose anymore, you'll have to kind of re-engineer the whole thing, replan, hire engineers, break their head, people reading other people's code. That's messed up. So instead of that, you can just give newer examples, and neural networks will train themselves, and it kind of abstracts away a lot of all these other things which could possibly waste time if the software architecture is not planned properly, way well in advance. So what exactly are artificial neural networks? So they kind of biologically inspired from our actual neurons, like what we have in our brains, but we don't know what happens in our brains. Like it's a fact. So neuroscientists have no idea why we do a lot of things, why certain things work the way they do. So back when Hinton, one of the godfathers of modern AI, he was working on his PhD thesis. What happened was his okay, I'm going to stop the history lesson in like 5 minutes. Okay, so we'll get to the code if you're anxious. His PhD advisor used to kind of tease him about when his neural networks would be relevant. So I would classify them, artificial neural networks, as a caricature of actual neurons. And a really good analogy would be to see that biological neurons, like our brains, how they function, are like a normal bird, whereas a deep neural network would be like a fighter jet. It does one task specifically, one task really well. It outperforms most humans, all humans. So, but there are lots of things which birds or wetware can do, which you literally cannot make. Deep learning, deep learning cannot compete with that. So one thing we're really good at is generalizing. So we can apply our knowledge, our brains, to kind of a lot of different fields, basically, without losing any breath. So what we're doing right now is, okay, I'm just going to skip over this so that we get to the. Basically what we're doing is, an artificial neural network is a set of matrices, if you're familiar with linear algebra, and you perform a lot of operations on them and have things called as activation functions, which are used to kind of manage the values into a small space, like say 0 to 1 or whatever. And we have a couple of examples over here of activation functions, sigmoid and tanh. So if you see, sigmoid pushes down all the values to 0 to 1. And these activation functions are used, like, they have their own properties, pros and cons. But in an LSTM, both of them are used in structures called gates, which are inside an LSTM. So what exactly gradient descent does? Gradient descent is an algorithm for optimizing neural networks. So the objective is to find the minima of a space. So it's trying to go to the bottommost portion of that graph over there. And it needs to keep a lot of factors in mind. So like the speed at which it's moving and how quickly it has to find it. So most of the time, space is not so easy to kind of find the minima. You have a lot of really complex spaces where you might be stuck in a local minima rather than a the global minima. So there's a lot of other flavors of gradient descent which are used, and they all have their pros and cons. I'll get into that. So the picture I showed over here, that's a vanilla neural network. So there's a variant of it called recurrent neural networks, which were designed to kind of introduce memory into the neural network. So to have some memory of what happened before. So in theory, they were supposed to remember a lot of things from the past and use that to influence decisions while doing it right now. So what it basically is if you unroll a recurrent neural network, it's like just a normal neural network in different timestamps. So each t-1, you see one over here. And so if you unroll it, you can kind of get a sequence of normal neural networks. So there were lots of problems with recurrent neural networks because they couldn't handle something called as long-term dependency. So suppose if you had a lot of data and some data which was in the beginning would be really crucial for some decision which you have to make in the end. Suppose you're reading a book and some information was in the beginning, the first chapter, and the climax of the book depended on it. So those kind of things, like normal recurrent neural networks were not able to learn. And there's other problems called like vanishing gradients and exploding gradients. So the gradients had this weird tendency to roll into themselves, either become really huge or vanish and go completely into nothing, like, as in a value of 0. So exploding gradients can easily be you can kind of cut them off and make sure it goes to a new 1 or something. So, but LSTMs fix the problem which RNNs could not do, which is the vanishing gradient problem. So right now, to dive into the code, the libraries we're using are Keras with a TensorFlow backend. Now it's heavily integrated, and NumPy. So I actually had the good fortune of meeting the author of Keras at the TensorFlow Dev Summit last year. The summit is again happening, I think, in March. You guys can sign up for it. It's in California. So what happens over there is that you get to meet the entire team, and you get a lot of inside info when you talk to them. So I talked to the guy who created TensorBoard, the visualization part of TensorFlow, and he told me that the person they asked to create the visualization actually listened to Joy Division, and the album cover of Unknown Pleasures was actually used as a visualization technique in TensorBoard. So yeah, it's the fun part. So the code. So we're importing a few key modules, and NumPy system, and then NumPy utils, and we are taking in a lot of other portions from Keras as well. So we're using what we're trying to do right now is, in a text file, we're going to put in basically ASCII characters of whatever you want to train it on. Suppose you want to train it on Shakespeare, the entire collective works, you put it in the text file and save it. So for what we're building, something close to at least 1 MB to 10 MB would be good for training LSTMs. And so you open it up and you convert everything to lowercase. So the problem is, since these are pattern recognition and replication machines, they have no idea of what context is. So capital and lowercase letters look the same. So in order to give some uniformity, you convert everything into lowercase. So then the variable chars or characters, what you're going to do with that is take the unique characters which occur throughout the text file, the corpus that is. So with that you get a vocabulary. So it's like most of the time you'll get A to Z letters, and you might get special characters, you might get numbers. So and you're creating two separate dictionaries which allow you to convert the character into an integer and back. So if you had, say, 40 different ASCII characters in your text, it might be exclamations, normal alphabets and stuff, then the size of the dictionary would be 40, and each one would have a unique number assigned to it. And so this is because we're going to create one-hot encodings of all these characters and then feed them into the neural network. The reason we're doing one-hot encodings is because neural networks speak the language of linear algebra, so vectors fit in perfectly. They can't do anything with raw text. So to get your corpus, you probably have to do a lot of things, because consolidated data is not available very easily. So you can use scraping libraries to either take it from different websites or from Twitter. Twitter's API is very limited. I guess you can't take more than 8,000 tweets from one account, and it doesn't help much because it's just 140 characters, right? So you'll have to do a few things to. Otherwise, you can use an existing data set. There's a few of them available, and you can also convert PDFs to raw text. I had to do that for a couple of times. So right now we have two variables on top. So first you're taking is the number of characters that occur in your corpus. It might be like 1 million or 2 million characters. And then you're also taking into account the size of the vocabulary, which is the exact same as the number of characters. So that's why you're taking the length of the variable characters. So so we're defining a sequence length of 100. It's arbitrary. You can choose anything. So I'm just using 100 for this example. So now we have two separate lists. What we're going to do is kind of have a sequence where you have 100 characters, and you have one character which happens after that from your text. So it's kind of to give historical context to that specific character. So what you do is, if these 100 characters are given to the model, then this should be the output. So it understands that all these 100 characters played some sort of a role in making sure that that was the one which followed it. So what we're going to do is create lists of these 100 character sequences or patterns, and the one character which comes after each one of them as the output. So that's why you have sequence in and sequence out. So then what you do is you convert them into the integer mappings we gave just a while ago, and then you have a list of lists for data X, and data Y is just one list. So the number of patterns you get, it basically starts from the first. If you see, there's a for loop over there. It starts from the first 100 characters, and then the 101st character is the first output. Then it slides the window by a step of 1. You can change the step if you like. The last one, the for loop parameters. So that's a step of how many windows to slide every single time. So right now, those 3 lines of code, what they do is they convert each of them into one-hot encoding. So what are one-hot encodings? So these are vectors, all of the same size, and the one which you want to represent, like with the same character to integer mappings, instead of having an index from 1 to 10 or something, you would instead put the value 1 at the location of that index. So for A it's 1, and for if Z is the last one, that would be the last one in that particular thing. So we're kind of creating uniformity in all of these vector sizes before you feed it into the neural network. So now we're going to build a model. So we're going to add an LSTM layer and drop out dens. I'll explain them in a few moments. So after that you're creating a file path and mentioning the epoch, which is an epoch is basically one whole the time required to go through the data once completely. And then you're also storing, so you're storing it in the format of HDF5. These are weights which you use to these are the weights of the matrices which, while neural network is training. So why would you want to save your weights? That too periodically is because neural networks, training them is computationally really intensive. So what if you have a power failure, anything like wrong happens, you'll at least have the most recent step where you saved it. And then you fit the model and you run it for 20 epochs. So coming back, so the LSTM layer, I guess it should be kind of clear. But what is dropout? So dropout is kind of like a technique. It's a regularization technique by which you can help stop something called as overfitting, which is a huge problem. So overfitting is basically like if you see this graph over here. So what happens is, if you want to create some sort of a model which separates all the red and blue dots, show of hands, who thinks the black line is better, who thinks the green line is better? Black. Yeah, so black is definitely better because it does a really good job, as well as it generalizes. So when we say something learns, when we say a machine learning algorithm learns something, it learns how to generalize something. So if you see the green line, it is perfectly fit to kind of consolidate each and every point in the right way. But it also memorizes the exact locations in this thing. So it's kind of like just memorizing before an exam. It doesn't help you. The exam questions are different. Instead, if you have a better way to kind of separate it, you might make a few errors, but at least you know what's happening. You understand that these are red, these are blue, and you can only separate them in this way. And if you given like a new set of spots, you can also do to a really good degree. So how this helps is with dropout, you train an ensemble that is a lot of different times. You train neural network with a few of those nodes kind of absent. You don't include them. So what this does is that once you average them out, some like single neurons or single nodes won't have the kind of influence of memorizing a specific thing. So it curbs the influence each neuron has. So when it does it randomly over multiple iterations, it kind of learns to generalize much better. So and we use the softmax activation function to kind of change the vector into probabilities. If you see over here the last one, these numbers change into probabilities, and all these numbers add up to 1. So the one with the highest probability wins, as in that's the most probable character. This is a good example. The input is H, and the output, the most likely character is E. And if you see the vector, the first four, the only four rows is H, E, L, and O. So the green one shows which is the one which won out. So after H you get E, after E you get L. So it kind of learned how to say hello. So this is on a small scale how it might work. And when I talk about optimization algorithms, there's different kinds. So this is a nice animation showing how each of these variants of gradient descent work. So some of these are called saddle points. Like if you see the red one, it kind of just hangs in there. It's not able to go down. So again, depending on the data, depending on a lot of factors, you have to choose the right optimizer, because that could mean the difference between like minutes, hours, or even days. Because if you choose the wrong one, you might have to wait for your algorithm to train. It might be stuck in that minima, and you'll never know. So now let's use a model which was trained to generate some text. So file name, I mean, you'll have to pick the one with the least loss value, and then you load it. So what you're doing right now is you need to have some sort of an initial sequence to give as a seed to predict the first character. So what we're doing is from the list of patterns which we had before, we're taking a random number and using that as a seed value. And if you see the print over here, we're printing them out as characters, because if you remember, we saved them as integers before. So now we're going to generate 1,000 new characters. That's why the loop goes to 1,000, and you use the predict one character using this pattern. Like you give this 100 characters, you get one output, and then once you're done with that, you output the result, and you attach this new predicted character onto your pattern and remove the first one out. So it stays consistent. You still have the same 100 characters again, but it's just updated with a new one. And use that to feed it back in and generate the next character. You do this 1,000 times. And why I used sys.stdout.write instead of print is because print formats everything. So if you format each character while printing it, it'll print one character, go to the next line, and do a lot of other things. So you don't want that to happen. You want the text to come in a sequence. So once you go done with the 1,000 iterations, that's it. So if you want to have a better output for the larger data set, also one interesting thing you might have noticed is we use all of it for training. We don't have a testing data set because there's no objective way to test how good the output is, because it's all subjective. So there's something called as the ELIZA effect. ELIZA was this AI program which was written in the 60s or 70s, and people use it as a chat assistant, and it was supposed to break the Turing test. So a lot of people kind of interpreted whatever ELIZA said as actual thinking, and fell into the trap that it had some sort of intelligence. So we humans have this thing where we anthropomorphize every single thing we see. That's why robots have hands and legs like us. They don't need to have it. I mean, that might not be the best thing for a robot to do, but we do have them because it makes us feel, it makes us empathize with them better, I guess. I don't know. It's a crazy thing. So other things we do is, the crazy thing is that we have this notion that we can create something better than ourselves, like an AI which general artificial intelligence, that is. So it requires some sort of hubris that you can build something which could outperform you. I don't think that's possible. A lot of people do think that. So so if you want to go deeper, you can just add a new LSTM layer just by just using model.add. So Keras is so simple that you can just stack layers on top of each other. And it does away with all the low-level details. You can focus on just the high-level details and build your prototype the way you can. So this is one example of what we did at the lab. Anybody watches Rick and Morty?
Yes.
Yeah. So this is one episode where the main character, Rick, he kind of wants to create a morally neutral world leader. So what he does is he combines the DNA of Abraham Lincoln and Adolf Hitler because he thinks they represent the extremes. So he wanted to create somebody who was perfect, not too bad, not too good. So what ends up happening is he creates this guy called Adolf Linkler, who is a paradox, a walking paradox. He says stuff which contradicts itself. So for training this, I took the entire speeches of Lincoln and Hitler, put them into one text file, and this is actually a Twitter account. There's not many followers, but yeah. So I'll read out a couple of these. In 1918, I am the warfare, struggle of civilization, the only answer to absolute liberty, is the destruction of nations. So it's very, it kind of learned the essence of it. And I'm pretty sure a lot of you might have worked with hidden Markov models and Markov chains. You might have heard of them. So they're also used to generate new text, interesting text like this. But why these things like LSTM is superior is because of the long-term dependency factor. So if you train Markov nets over same kind of data, it does not learn a lot of the long-term correlations. So some people trained an LSTM on LaTeX code or the source code for Linux, and it is able to generate code which is actually compilable. So if you got that code out generated by this this model, you could compile it and it would throw no errors. The reason that happens is because it keeps track of all the brackets. It knows that brackets have to be closed, and it knows indentations work this way. So that kind of deeper level of learning can't be achieved by simple Markov models. You have to kind of significantly modify them. So that's the issue. But if you have to modify it, you have to put a lot of thought, a lot of work, and kind of create something new which probably doesn't exist. Instead, you can create something which should do the job for you, which will learn much faster. So that's why that's why there's a lot of hype, because of the results. And this undeniably sounds real. It sounds like but this is the Eliza effect again. So in the end, the output which comes is like thousands and thousands of characters, and you see the ones which are funny. So I saw the out of the output, I took excerpts which are funny and I put it up. If I just make it automated like a bot, it would make no sense. So that's how these things work. So there's a few more outputs. I could not destroy. I would be ready to suffer. So, and this another thing we did with this is train it on this local Indian celebrity, and it also learns hashtags pretty well. Because hashtags are real. Yeah. So KRK is this notorious celebrity who speaks a lot of nonsense. I mean, it's not. It's just interesting in India. So the next one, since I guess the file doesn't load here, what I'm going to do is we trained it on MIDI data. So with this, we're able to actually generate music. Let's play it out. So, hope it's audible. So if you notice, it's kind of mostly in key, and it sounds melodic. There's a few times where it goes off key. Maybe a little more data would solve that. So since MIDI can easily be converted into like an ASCII format, you can do this with a lot. And the cool thing is, this is language agnostic. You can put Chinese characters, you can put any language. It is still this is part of the data. And since language is like a shared social construct that we all believe in, and you can just put anything in, see the results, interpret it in your own way, and that's why you have no testing process over here, because there's no objective way to do it. Okay. This snippet is from the official Keras example text generation. There's other parameters you can play with. One is temperature, which kind of controls how unique the characters are. Like a low temperature would mean more likely but more commonly used vocabulary terms. Like if you arrange all the letters in terms of frequency, the ones which are most used would recur more if you use a low temperature. And you could also there's a parameter you could try called priming text. So instead of choosing a random seed value for those 100 characters, you just give your own sentence and ask it to complete it. So it completes sentences essentially. So that's actually about it. Any questions? Yeah.
So this question is from...
No, it's fine.
Yes. I probably missed details, but I was just wondering why you chose to look at characters as you're doing some analysis.
That's so. There are word level models as well. So this is just an example because it's easy to cover in this talk. So that's better.
Or why, for example, why not words?
Yeah. So why not words is because if you have characters, you know that there'll be like 26 at least, and there'll be like 40 of them. Words you need to have like a larger vocabulary. So more training time, the model will be a bit more complex. So So for a easy example, this trains pretty well. So like on this MacBook, which doesn't have it's a really bad GPU, it's an Intel GPU. So it takes 10 hours to kind of train it well to get coherent output. But if you, I'd suggest you could check out this website called Floyd Hub, FLOYDHUB. It's like Heroku for deep learning. It kind of takes care of all the installations and all that. So you just create an account and you get say $100 in credit per month, and you can train all your models if you don't want to,
What kind of languages or packages does it?
It has everything, all of them. PyTorch, that is everything. It's already pre-installed in that. So they try to make it easier for people to get it. Anybody who's interested can come and take this. Oh, that'll be kind of difficult. Okay, who asks a question gets one. So you can choose one. Anybody else?
Yeah, I have a question. You're using gradient descent, right?
I don't understand.
You said that you're using gradient descent.
Yes.
Which actually the algorithm you use is gradient descent. So
Yes.
the problem, what I'm thinking is that since it's about language, it's like there's probably like really big data set that you need to do, for it to learn. So how will you determine? Because for example, if I'm using sequential data like date ranges or something, it's easy to identify if I overfitted or underfit my data.
So yeah, overfitting and underfitting you only know when you see the output, and it takes human intervention to know whether that happened. You can't estimate it.
Okay, so what are the
So
key
overfitting,
points?
how you see is if it basically reproduces, suppose you're generating new Shakespeare text, but it instead quotes actual lines, then it's overfitting.
Okay. Okay, that makes sense.
Okay.
Okay, thanks.
So either you need to have lesser data or make the net bigger, kind of accommodate for that.
Okay.
So again, like you're not memorizing. So if it quotes exact lines, then it's not learned how to generalize and see patterns, how that person's style was. So style is basically just a consequence of learning patterns. So that's why since humans tend to look for meaningful patterns, that's why this is interesting. Otherwise it's not.
Yeah, because it's subjective.
Yes, it's subjective, exactly.
Okay.
You can have a sticker once you get out. Any other questions? Yeah.
So, because I'm thinking, what's the expectation in the machines that you actually use to run the training?
Okay, if you have there's a lot of NVIDIA GPUs which come installed with CUDA. So not didn't come installed, like if they support it and you can install it, you can search for those. They're kind of I wouldn't suggest buying one specifically for yourself because you'll probably have to buy a PC. And the laptops which have CUDA enabled chips are huge, they're like 5 kilograms or something, and they can run. So the better thing would be to rely on the cloud. So either you can create your own AWS instance. So if you don't want to deal with that, Floyd Hub is pretty good. You don't need to worry about that. So on Floyd Hub, the same thing would take a few minutes to train, I guess. Yeah.
And for storing the amount of the model, does it take a huge amount of space to actually store it?
Yes. So you're basically storing the weights, right? So depending on how big your model is, the sizes can be huge. So sometimes when you have like if you have like a image classification model, some of them are like 700 MB, some a few gigabytes. So it depends from what is learned.
But in your experience, what's the actual range that you encounter?
It depends again depending on the problem you're trying to solve. So and yes, that's about it. So hard limits. Anybody else? Okay, that's about it. Hope you guys enjoyed this. Thank you again for putting up with all of this. And if you would like to ask questions to me personally, I'll be available.